Thank you. Good morning, all. I think most of you were
Yeah,
on the
I think we can
original, sorry,
start.
the previous call we did on urban drainage,
Yes,
and
should be okay.
the next
Super.
in this sort of series is 2D structures. So we've got a fair few slides. Like Arno said, feel free to ask questions as we go along. I'll try and keep an eye on the chat and the Q&A as I present. Yeah, we'll crack on. So the plan is to cover the following structures. So we'll start looking at, we'll focus on 2D bridges, but it's, a lot of what we talk about is applicable to culverts as well. We'll then look at 2D weirs, a couple of other common structures, and then we'll end off by talking about breach modeling. So we'll talk about bridges. Like I said, this also covers culverts, basically anything that takes flow through an embankment, where we might have a structure over an open channel, for instance. So water has energy as it flows downstream, as it flows downhill, and as it flows downstream, that energy is dissipated primarily as heat. And there's two components here. The first is bed resistance as it flows along those open channels, which is usually represented using Manning's N. And then the second is the change in flow formation, which occurs around bends and constrictions. So we can see in the image here, we have, just turn my pointer on. Sorry, on the video here, we have flow coming down. We have this contraction of flow through the opening, leading to some energy losses. And then we have the expansion of flow downstream with associated energy losses as well. So here we have a loss of kinetic energy. And bridges can cause, as we can see by the animation here, quite significant changes in that flow formation. So we have quite a bit of contraction losses, quite a bit of expansion losses, and that causes significant form losses. All in all, the bed resistance component here is relatively minor, if not negligible. So it's the form losses that are more significant in this instance. What you might be able to just see as well is there's a couple of stand or bow waves just upstream of some piers as well, so they're significant as well. What have we got in terms of form losses at bridges? So they're varied, and there's a couple of components which can contribute to the total form loss. There's that embankment side of things, which we just talked about. So it's basically a constriction with contraction upstream and expansion downstream. We have our piers, and basically this is just another form of constriction. We can see here we've got a water level, a bow wave at the upstream end, and some turbulent flow downstream. We have overtopping. So if our bridge deck becomes surcharged, we have energy losses associated with that overtopping. And then we have the actual deck itself. So the deck is a blockage, and that also leads to pressure losses as flow goes under the deck and generates pressure onto the deck. So I'll go through these in order. We'll start off with embankments. So as I've alluded to quite a few times already, when we're looking at bridges, there is a significant amount of contraction and expansion, and we need to represent that in any approach that we use to model them. So we can use 1D, and this is how we've done it in the past, although this does require a bridge model, because we need to represent those entrance and exit losses. They can't be represented using 1D hydraulics. So we have various entrant losses to represent the contraction of flow. We also need to represent the vena contractor, which is this component here. We need to represent those. Then we have to represent our exit losses, which represent that expansion of flow on the downstream side. So when we model these in 1D, we need a bridge model. We need to represent our afflux, our change in water level, and essentially we use an entrance and exit loss coefficient, and we apply that to our velocity head, and that's what determines our afflux or head loss through the structure due to those contraction and expansion. With 2D, that contraction and expansion is represented explicitly. You know, the 2D hydraulics can represent flow coming down, hitting an embankment, and then having to contract through the opening. So those kind of losses are already represented. So we don't necessarily need to worry too much about them from a 2D modeling perspective. What is less well represented with the 2D approach is this vena contractor. We don't necessarily represent that particularly well. And also with our 2D approach, it's a depth averaged approach. So any losses in the vertical and variations in the vertical, we can't represent those using a standard 2D depth average solution. Bridge piers, they form or another form of constriction. So they do squeeze water between them. And there is a drop in energy levels, and we can see that here. So we have the top of our bow wave. We have downstream where our water, you know, there's a bit of turbulence, but it's relatively still. So we have to represent that energy loss associated with the presence of that pier. So in 2D, you know, there's two main options. The first of which is we model our river in 2D, and we use quite a coarse 2D mesh, and then we apply a form loss coefficient to that to represent the energy losses associated with those piers. What we typically use the KP value from the hydraulic of bridge waterways document. That hydraulic of bridge waterways document is commonly used for the 1D modeling of bridges. So we use that and we apply that to our 2D cells to represent the losses associated with the piers. There is a question of how you apply those KP values. Should it be applied across the whole waterway, or do we factor it based on the, apply it to the actual piers itself? So there's a couple of bits of guidance on our wiki pages which go over that, which I'd recommend reviewing if you ever need to go down that route. The other way of doing it is to model the piers explicitly within the 2D mesh. So with things such as Quadtree, we can now nest down the grid resolution. So we can actually start to model some of the details of the piers by representing them explicitly. It is quite difficult to do with a fixed grid scheme, but like I said, with Quadtree and also subgrid sampling, it does help quite a bit. You do need a very good subgrid turbulence model, and one that's suitable for those situations where the cell size is less than the flow depth. So we do need to consider the turbulence parameters. And all in all, we can get similar outputs in terms of afflux between the two methods. There's a link there, and I'll allude to this at the end of the presentation. But this is a webinar that a couple of my colleagues did for the Australian Water School, which goes through some of this representation of piers, both within using a coarse 2D mesh and applying form losses, and also representing using a very fine 2D mesh. So I would recommend, if you are looking at modeling piers, that webinar is very, very useful. Finally, we have the overtopping, both of the embankments and the bridge deck itself. So this is usually represented by treating the flow over the top as either upstream or downstream controlled weir flow. So it starts off as upstream controlled. We have shallow flows going over, so we use the weir equation. And then as our downstream depth starts to increase, the weir starts to become drowned out, and we start reverting to the normal flow equations. So we do need to handle both flow regimes, both the upstream and downstream controlled, and also that transition as we submerge the deck and those embankments. It's fairly standard for 2D software to model this kind of thing automatically. So, from a point of view of embankments and deck overtopping, that's fairly standard. So all in all, we have the energy losses or the form losses in terms of bridges, we have those that contraction, expansion of flow. We have the pier losses, and then we have those losses associated with overtopping. So those are the kind of things that we need to start representing. So how do we do this in TUFLOW? Well, like I said, the 2D hydrodynamics does a pretty good job of representing those contraction and expansion losses into and out of the bridge opening. Where we need to focus our attention is on the specification of additional form losses to account for the piers, decks, and railings. And what we do in TUFLOW is we use a 2D layered flow constriction. So this is one of the layers that's available within TUFLOW, and this allows us to represent various different blockages, represent different form losses in the vertical plane. I mentioned, modeling bridge geometry explicitly. We can do this, but it can become inefficient. So obviously, if you are representing the piers, you do need to use quite small grid cells. If you're using small grid cells, obviously that's a small time step, and that can lead to quite long simulations. There's a 3D component to this. Obviously, when you've got decks and railings, they vary in the vertical, so they can't be that easily defined using a standard 2D scheme where we're trying to model the bridge geometry explicitly. So we do use these 2D layered flow constriction approaches. They allow us to vary the blockage in the vertical, and they generally produce a much more accurate water level afflux result from them. And ultimately, from the point of view of flood modeling, that's what we're interested in. So in terms of the 2D layered flow constriction, we essentially can split up our vertical for each cell into 4 areas. The first of which, layer 1, is the below deck situation. So we specify the blockage associated with the piers. So these piers account for a 10% blockage across the length of my layered flow constriction line. And then we apply a form loss coefficient to those. We then have our deck. So in this instance, we specify our soffit level where our deck begins. It has a thickness. In this case, our blockage is set to 100%, and we have a form loss coefficient associated with that. We then have our railings, so we can have a blockage associated with that. This is set to 100%, which seems a bit over the top in my eyes, but again, we could vary that depending on what the blockage to the flow area is. And then we have everything over the top where we have 0 blockage, and we don't have any form loss coefficients to that. So we can represent the various layers within the vertical using this layered flow constriction, represent the different geometries by applying a blockage ratio, and then also applying individual form losses to it. So the 50% or 10% pier blockage, for instance, reduces the flow area of those cells, constricts the flow, and leads to higher velocities. We then need to add that in conjunction with the form loss coefficients, because these are what represent the subcell losses. That's what we need to represent the wakes behind the piers and the wakes behind the decks and similar. This is how we would go about setting one up. So if our bridge deck is represented in our topography, we might need to use a 2D Z shape to take that out and have a clear opening. We can then specify a 2D layered flow constriction that can either be a line or it can be a polygon. You'll see there we've got an invert level of 99959. And what that means is that we're not adjusting any of the elevations. We're taking those from the existing ground level. In the case of a culvert, we might use that to set the invert level for the opening. I'm just going to see. This is the pain of doing it this way. We'll go through them individually here. So, like I said, We read in the GIS layered flow constriction shape. That can be usually a polygon or line. You don't tend to use a point. We set the invert levels. A value of 9999 uses existing Z point elevations. We can adjust the elevations if we need to, and we can set a shape width. So this is the number of cells that the layered flow constriction is applied across. So we can use the various commands. We can represent over multiple cells. And what we're doing here is we're not changing any cell storage. We're just changing the fluxes through the cell faces. We have this shape option. So this defines how our losses are represented in the verticals. So we obviously split our different layers, and then we could either accumulate them, we can proportion them over the depth, or we have this method C, which is kind of a combination of the two. And I think it's the portion approach, which is the default. So we have the losses, they're uniform up to the deck. Then our values change proportionally, and then we have, again, it changes proportionally to depth as well. So this is, as I'll show in a minute, kind of the well, that's the default, and based on our testing is the usual approach to doing this. We then specify our geometry of layer 1. So we apply a soffit, which is essentially the deck level. We apply our blockages, which is our pier blockage, and then we have our form loss coefficient associated with that first layer. We have layer 2, where we specify the deck thickness, and again we specify a blockage, and again we then apply a form loss coefficient. And then finally we have layer 3, which again we specify a thickness, a blockage ratio, and a form loss coefficient. Everything above the layer 3 thickness, so we specify an invert level, we've got a soffit level, we specify a thickness, and then the thickness. Everything above this level is just treated as being unimpeded flow. Where do we get the form loss coefficient from in terms of the pier losses? That's usually taken from that hydraulics of bridge waterways document. Like I said, this is a commonly used approach for 1D modeling. We calculate the reduction in cross-sectional flow area due to the piers. And from that, we then pick the relevant curve to do with the shape of the piers, and we read off this delta Kp. And that's what we apply to our form loss coefficient value. That's used with the velocity head, and that's what determines our afflux. So from a pier loss point of view, this kind of theory and the parameters used is pretty well known. What's less well known is the guidance of the form loss coefficients for decks and rails. So that those are a bit more of a black art. However, we've been doing some research into this area with the Department of Main Roads in Australia, which I'll go over briefly now. This is the work that we've been doing with the Department of Main Roads. We started off doing some 2D CFD modeling of some quite simple bridges. So these are pretty simple decks. Quite standard for what happens within, or what bridges exist within Australia. We have the flow, we have our deck, which has 100% blockage. We have these rails, we have this little lip as well. Obviously, the blockage provided by that deck provides a wake. We have the vena contractor downstream, and then we have, we can model the surface waves upstream. So we end up with a head loss, and we can see what's going on quite visually there. We did a range of tests, and we started to come across this quite familiar curve shape. It seemed to be quite consistent, where the head loss was related to the tail water depth for a range of bridge deck thicknesses. to go back to this, we modeled with a range of bridge deck thicknesses. That's the T value. And then we had the tailwater depth. So we found a relationship, or seemed to construct some kind of relationship between that. Question was whether we could non-dimensionalize that. So we did that. We put TW over T, and we looked at the loss coefficient. And we've got quite a nice grouping of the curves there for a range of different scenarios. And we found that the peak loss coefficient occurred at around 1.6 times the bridge deck. So we started to go away and we started to think about how we can apply this in terms of modeling bridges. Quite opportune that there came an opportunity to get some observed data in. So we did some full-scale bridge measurements. This is a real-world data set. This is one of those. This is the bridge that was studied. It's quite a common Australian bridge. We've got the deck. There's no piers. We can see this little lip again that we saw previously. We've got some railings going on. So simple deck and rail bridge, minimal embankments in this instance, no piers. And what was quite useful about this bridge is it has low immunity. It floods quite often, about once a year. It was also well censored. So upstream and downstream water levels were installed in 2021. These were calibrated, and then the data was made available to the TUFLOW team and the Department of Main Roads, who we were doing this work with. And quite fortuitously, in February 2022, we got quite a nice flood event. Upstream went on for about 60 hours. We can see that we've superimposed an image of the bridge on here, so we've got the deck and the openings, and the railings, and we can see that for the for this 60-hour event, 3 days worth of event, that most of the time it is over the top of the bridge. We managed to get out on site and get some videos. And this was about the period that we took the video. Sorry, I've just seen that there's a question. Not at the moment. Sorry, the question is it possible to define the L1 obvert in relative H above bed invert instead of absolute Z? No, it's not at the moment, although this is something that I noticed a month or two back, so I have requested it as a something that we do allow.
We had a few other questions. Do you want to go through now, and then we can keep?
So the one about the arch bridge, if I can come back to that one, that would be great, because I'll mention that a bit later on. And then
subgrid turbulence.
Subgrid turbulence. I'm not sure I completely understand that question. So the subgrid turbulence is essentially the subgrid level hydrodynamics. So TUFLOW has a range of subgrid turbulence models which can be used. The latest default with TUFLOW HPC is the WU turbulence model, and this has been chosen because it displays, well, it has a representation of 2D and 3D turbulence, and it displays pretty similar turbulence parameters across a wide range of cell sizes. And obviously, from the point of view of something like Quadtree, where you've got the ability to vary cell sizes within the model, you do need to have pretty consistent turbulence parameters. It's also possible to use a constant turbulence model and a Smagorinsky turbulence model, but the WU is the default option that's within TUFLOW. And unlike other solvers, the turbulence model is switched on by default. Quite a few other solvers will have a turbulence model present, but they don't switch that on. by default anyway. So the TUFLOW does have that, and it is switched on by default. I'll come back to the arch bridges shortly.
Okay.
This is a video.
Sorry. Wait. Yes. If we can come back for the arch after that, I think there may be two questions behind the arches. Is the one that Quentin asked? Is how do we deal with these bridges which are not rectangular? And is there some easy way to calculate the surface and the layer one area available? So we can, if we can keep these two questions in mind.
That would, yeah, that bit of it would need to be calculated externally to TUFLOW.
Okay. Thanks.
No problem. Sorry. So this is a video pretty much at the peak. So we can see we've got, we can just about make out the road there. Bridge is fully submerged. We have, quite a few surface waves over the top. This is slightly lower. Again, you can see the road. We can see the flood marker. Deck submerged, but we've got some of this plunging flow. We've got a standing wave downstream. At this point, lower still. You can see the gauge marker there. You might just be able to make out the top of the railings, and you can see we've got a bit of debris here. And a bit lower again, definitely pretty much see the deck now, and we can see the railings, and we still have that quite significant bit of debris there. Went out on site. We wanted to get an idea of the debris and survey that, but in this case, although we went out pretty much, I think it was the day after the event, the local residents had already removed that debris. So we were not entirely sure how much debris was present during that event. We built some 3D CFD models of the bridge, used this to assess the observed data accuracy. So we used both Flow 3D and also Open Foam, use slightly different turbulence models in each. And what we did is we plotted up the gauge data, and we also put in the results from the CFD modeling. It should be noted that in terms of the open foam results, we didn't have enough time and budget to do all the water levels. Obviously, the CFD simulations take quite a long time. We didn't have the budget to do that. We ran out of time. But again, we showed that the afflux as a result of the bridge was a function of the tailwater elevation. And what we've done here, we've got downstream water level here. We've flipped the image of the bridge again, but we've got that same general curve that's going on, and that was replicated with the CFD models as well. So below the soffit, no energy or losses associated with the deck. We then have the energy losses, and once the water levels get to roughly 1.6, then they start to recede. We built a TUFLOW HPC model of this, and we again used the flow layered flow constrictions. So we had one loss coefficient up to the bridge deck, and then we linearly transitioned from that pier loss coefficient up to a peak loss coefficient. And then we had that decay, and again we were representing that very generic curve that we've seen from the previous models. So we've got a good correspondence with the observed data. We've got a good correspondence with the CFD models as well. What 2D 2D shallow water equations don't do a great job of is the surface waves. So what we've done here is you can see the solid lines of the surface waves, whereas the dotted lines are the energy levels. So we use the energy levels in a way. So we would use in this to generate a common parameter set. But what we also did was, rather than using a layered flow constriction layer, is we actually set up a new 2D bridge layer. So this is a slightly different layer to the layered flow constriction. It's got some similarities. We specify our ID. We specify our option again of how we deal with the losses, whether we accumulate them, whether we portion them, or whether we use a what's called a method C approach. Again, we specify the pier blockage or the pier form loss coefficient, but this time it's explicitly stated as piers. So it doesn't say layer 1, layer 2, layer 3. It says pier, and then it says depth. So we specify our piers, specify the deck soffit, the deck depth, the deck width, which I'll come into in a minute, and then the deck blockage. And then we specify our rail depth and our rail P blockage. So, these are pretty much the same parameters that we had for the layered flow constriction. But this time we're not specifying a form loss coefficient for the deck or for the rail. We're treating this as what we call a superstructure, which is an absolute terrible name for it. But that's what that's what the developers looked at and thought, we'll call it a superstructure. So our form loss coefficient is for that what's called a superstructure, and then we've got this inflection point, which is the point, the peak form loss coefficient, and then it starts to decay. So default is that 1.6 that we saw previously. So if we look at the form loss coefficient with height, below the deck soffit, our form loss coefficient is constant. We then have a linear transition to the inflection point, and then we have this decay. So this is what our form loss coefficient looks like with height, and our total form loss coefficient is shown there. So that's what's going on. The deck width attribute. This is the distance in the predominant direction of flow. So essentially what we're doing is we're calculating the form loss coefficients and the energy losses, not on a cell basis, but on a cell face basis. So it's applied to the cell faces itself. And then the form loss coefficients at each face are calculated based on the deck width. And what this means is that our form loss coefficients that we apply are independent of the cell size that we use. So we can set up the form loss coefficients, and then we can vary our cell sizes if required. What we're planning to do in the future is to vary the pier loss and the form loss coefficient with the height, and also come up with some default peak form loss coefficients based on that TMR research. We've come up with some parameter guidelines. So, again, the pier form loss coefficient, we would recommend the hydraulics of bridge waterways. Excuse me, but that deck and the railings, like I said, we treat that as a superstructure, and we found that this is a function of the deck soffit to the deck thickness. So, that ratio, we have some suggested form loss coefficients, and that model, that real world example I showed just a minute ago, the Gordon Road Bridge, we looked at the ratios, depending on whether you took the deck on its own or whether you took the rails, that's the ratio, and we used a value of 0.28, which is about the same, well, it is the same as this scenario here. As was alluded to in one of the questions, this and the way that layered flow constrictions are set up are very useful for these kind of quite simplistic bridges. We don't have an approach to do arch bridges at the moment. We would be very, very keen on any data or that anyone knows about which represents these kind of things.
Okay.
What we have done for the 2023 release is add in an approach to represent arch bridges in the 1D domain. So this is the HR Wallingford arch bridge approach. So if you've ever used ISIS Flood Modeler or InfoWorks RS, this is the approach that's within there. That was based on empirical measurements on 32 bridges. I've actually done a fair amount of research on this over the last couple of years, and it turned out that I actually lived about a mile from one of the bridges that was used. It's not even an arch bridge, and if I'm completely honest, I didn't even think it was a bridge. I used to run over it on my running route. It's a culvert. So yeah, it's not the best approach. We've done a lot of modeling comparing it on a 1D sense to the TUFLOW bridge approach, the BB bridges and the B bridges, and also using irregular culverts, and they seem to be much better than this HR Wallingford bridge approach. But anyway, in terms of 2D modeling, not possible at the moment, but we are really, really keen to get data and do some testing on that kind of thing, so we can develop some methods to move forward. Yeah, ISIS rocked so much they renamed it Flood Modeler. We always used to joke that the terrorist group also renamed themselves Flood Modeler. So yeah, so that's bridges. I thought it'd be quite useful at this point just to mention 2D PO structure groups. So these allow you to use a series of plot output lines and points, and use them in conjunction to give you some or just an easier way to assess individual structures. So we combine, for instance, in this situation, we combine the plot output lines, which represent our structure opening itself. So with this, we set that to a type of QS, which is a structure group. It's got the label bridge. And then we also have some PO points and plot output points. They have the same label. So they've got a label of bridge. They've got a type of HD for downstream water level. At the upstream one, we have a same label. This time we set it to HU. That's how we set them up, all the same name. And then what that allows us to do is then to start plotting the results and see them in conjunction. So although we're only selecting the line, this would usually allow us just to see the flow through that line. So we can look at the structure flow, but we can also look at the upstream and downstream water levels. Stick them on the secondary axis, and you can start to investigate what's going on through your simulation and start to understand how that structure is operating in a bit more detail. It also gives you a bit more information about the total flow, the area, the average velocity for the whole structure, but also looking at the above, looking at through the opening and also above the deck. So it just gives you a bit more information with regards to what's going on in the simulation, but treating the structure as a whole. So that's bridges. I'm just going to have a quick look. There's one question in the chat. Bear with me. Is it better to use 2D bridge in case of a large bridge, up layer construction in case of thin bridge? Sorry, I don't really understand that question.
I guess Quentin?
Yes, sorry, it's not very clear, but I just was wondering up from what width value of the bridge it's better to use the 2D bridge representation instead of the layer representation. I mean, I understood that it depends of the width of the bridge, but do you have a value to decide if it's better? Yeah.
Yeah, I don't think it's a case of necessarily the width of the bridge. I think it's the new 2D bridge approach is more designed for bridges. So it explicitly calls things piers, decks, and the superstructure and rails, etc. So it's just easier to parameterize. Everything that you can do in the 2D bridge, with the exception of that superstructure thing, can be done with the layered flow constriction. So I don't think there's necessarily a case of that threshold where you would use one and use the other. If you are wanting to use that bridge approach, and obviously you've got to use the bridge approach. If you are wanting to represent that deck width and have it over a number of cells, then you would use the 2D bridge approach, but you can do that with a layered flow constriction polygon, for instance.
Okay.
So they do very similar things. It's just much easier to parameterize the 2D bridge because it's it's a bit more explicit that you're dealing with piers and other things. The layered flow constriction is a bit more generic. It can be used for fences. It can be used for hedges and similar. So there's just a couple of different ways of utilizing that. So it calls it layers. Just be aware of the nuances of that bridge approach in terms of dealing with the superstructure, not being able to specify the form loss coefficient for the deck and the rail separately, and also that inflection point as well.
Okay.
So that's the differences really.
Sorry, maybe just a quick question on what you just said on the fences. I think it's a big subject here in France on the integration of artificial fences, of trees and so on. Do you have any studies or any technical paper to kind of calibrate this obstruction? Because we tend to use more and more these obstructions to represent this kind of obstacle, which is not fully blocked, but it's always not really clear what should be the accurate parameters to put inside these obstructions.
It's a tricky one. I know there is a TUFLOW paper which Bill Syme wrote on flow through fences and also includes buildings as well, which I can pass along, which I'll just make a quick note of. It's an interesting one. It's something I've done a fair amount of reading back when I was doing my PhD, because if you consider flow through vegetation, it deforms a fair amount as your flow depth gets bigger and bigger. So there's a lot of literature, a lot of which comes from Holland and has its origins in dealing with wind through poplar trees along fields. So there is some science out there, but I've never seen anything really come through in terms of guidance.
Okay.
I think the main thing that we would do typically is to make sure that the blockage is set up correctly, or as close as you can get. You're never going to go out there and really get.
Right.
We always used to have some crazy ideas of having a white sheet and taking photos through the hedges and working out how much white you could see, but it never really worked. But I've never really seen any studies of that, but I'm probably 5-10 years outside of the academic literature on that one.
Okay. And maybe just a quick remark to close on the bridge. I put some comment in the conversation for the people working in the public entities which are following the webinar. I think it's really important, as you said, to make some measurements on bridges, and not only on just one side to have the discharge, but if we can get some very accurate measurements upstream, downstream, photos, everything, to help calibrate and maybe enhance the calculation of losses. I think it's a big subject because a lot of I think that not all the softwares are very clear about what they can do in the bridges area. We have a lot of black boxes saying, yeah, we can do everything in the bridges, but no.
Yeah,
So
I completely agree. And obviously what they've done in the US, with the hydraulics of bridge waterways, it's very, US Euro public road type bridges similar to the ones they have in Australia. In Europe we have a lot of different shaped arch bridges, often quite fancy, and they obviously have
yeah,
quite a historic element to them. The only real, well, there's a whole host of flume tests on arch bridges, but no real models. The only one I know of is that HR Wallingford approach, which, like I said, it was based on 32 bridges, of which I know at least 6 of them weren't arch bridges, possibly
culverts.
more. And there's a whole host of other complexities. So yeah, if anyone is involved in that kind of thing, we would be very keen to have a look at any data. And this is something I push to the authorities in the UK as well. So hopefully, with a bit of luck, we'll be able to get something coming out of that pretty soon.
Okay, thanks.
We'll move on to weirs. So weir flow across levees and embankment is modeled as default within TUFLOW. So where flow in the 2D domain becomes upstream controlled, TUFLOW will automatically switch to a weir flow approximation. So this has been in place for TUFLOW Classic for some time. It's also been in place in HPC, TUFLOW HPC, although until the 2023 release, it was based on a broad-crested weir approach, whereas TUFLOW Classic was based on TUFLOW's advanced weir approach. So from 2023, or the 2023 release of TUFLOW, the TUFLOW HPC now supports that full advanced weir equation within the 2D domain, just the same as TUFLOW Classic does. So we can set that up automatically. CF is a weir calibration factor. That is set to 1, but we can change that globally using the set WRF command, or if we want to spatially distribute that, we can use the read GIS WRF, and we can specify a vector polygon as to where we want to vary that if we've got a particular weir that we want to represent. Obviously there's other parameters that are there as well, and they are set based on a broad-crested weir, but again we can adjust those if we wanted to within the TCF to change them globally. Just to go back to the weir reduction factor, the default is 1. Obviously increasing that to greater than 1 will decrease the flow efficiency, and thereby making the upstream water level higher for a given flow rate, and the value of less than 1 will increase the flow efficiency. This is just an example. So what we have here is some break lines that have been added. We've got essentially this pink line's the bed elevation. We've got an upstream bucket and a downstream bucket. We have our weirs, one represented with the thin break line and one represented with the thick break line. And what we can do is we can model that and we can compare with hand calcs, and obviously you get a very good correspondence to that. So TUFLOW will take that into account. It will also adjust for the submergence too. Just a small little case study on how this kind of functionality has been used. So this is a small dam in Australia that falls within ANCOLD regulations. So it's managed by the Australian National Committee of Large Dams. And as part of that, there's a requirement for a routine or regular safety review to revisit the spillway rating curve. It should be a relatively straightforward task, but in this instance led to a bit of a can of worms. So this is the spillway, and they had a simple OG weir at the top end of that spillway, and they were looking at what the rating curve should be for that. They went and used the Weir equation and calculated what it should be. So they had a current rating curve shown in yellow, and they then calculated based on the Weir equation. You'll see that there's a whole host of lines, and it looks a bit messy. I've had to take out some of the client names and various names. We'll add some of the lines in through this. So they had that existing line, and they calculated theoretically. And then they went away and used HECRAS, and they used obviously the break lines in HECRAS don't use the Weir equation like TUFLOW does. So they used the 1D element for the Weir, and then connected that to the 2D domain at the upstream and downstream. The problem is that they had water levels. The problem maximum flood event is around 140 cumex. The dam wall is at 39.5 meters, and obviously they'd have spill at that level, which wouldn't be acceptable. So they went away, and this time they produced a full 2D HECRAS model with a very fine mesh over the crest. That gave a completely different set of results. So, we have the theoretical and the current rating curve. They had the 1D, 2D rating curve. They modeled it in 2D and ended up with a completely different rating curve. So, which one do we use? There's no consistency there across the values. So they submitted those results to the dam safety regulator, who basically came back and said, right, just use TUFLOW. So we went away. They came to BMT, who are the creators of TUFLOW. We did use TUFLOW. Obviously, as I've just shown, we used the 2D Weir equation on our 2D break lines. We also did CFD modeling of this, as did the client. So as we can see in this instant, so we've got the blue line, BMT CFD, the client's line, an orange one, the TUFLOW, this brown line, and we've got a much better grouping here. So it gives us a bit more certainty as to what's going on. It also shows that the TUFLOW approach using the Weir equation over that break line gave consistent results with that HECRAS 2D model with a fine mesh resolution over the top of the Weir. So although the HECRAS 1D approach didn't do a great job, there's some consistency between TUFLOW using the break line approach and HECRAS using that fine mesh over the crest of the Weir.
Sorry, what will need to be the resolution of the mesh for HECRAS? I guess that to be able to capture really accurately the OG and the Weir.
I don't know that, but it has. Yeah, like you said, it's got to be sufficiently fine. I would suspect, given. I go back. You'd be looking at probably 5 cells across there.
Yeah.
So obviously there's a downside to that, which is the simulation time. But although it does a very good job, like I said, the simulation time is going to be pretty prohibitive there.
Right.
But using TUFLOW, using that break line approach, we could have a relatively coarse cell size upstream and downstream. We don't have to refine the cell size over the Weir. We're just using that break line, and we still get the very similar results, which also tie in with the CFD results.
Okay.
Obviously, we've got something which is quite different to what was expected theoretically. And actually, what was found out was it wasn't necessarily the Weir. The problem was the downstream spillway. And basically, flow was convergent as far as the yellow dash line. And then you had quite a bit of constriction at this location. So there were a few issues with the rating curve as a result of that. That's Weirs. We'll now move on to other structures. So there's a couple here. I won't dwell on any of them in any real detail, but I will go through them. So the first is pumps. So we can deal with these either as 2D components or 1D components. So if that pump's pumping at a constant flow, then that can just be quite simply added as a QT boundary with a negative flow. Or we can actually apply a depth discharge or a head discharge curve. We can use an ST for depth or an SH for head, and use that to take water away from a particular location based on the depth or the head. And if we wanted to, we could apply that elsewhere within the model domain. So this is just using our 2D boundary condition points or lines or regions. We can take flow away, and if we want to, we can apply that elsewhere within the model domain. So this is a location not too far away from where I'm sitting, where there was quite significant flooding in 2020, just before COVID hit. And I drove past at this and they have one field which was completely underwater, this road, and they were just passing it into the downstream field. So obviously, we can represent that using 2D boundary conditions. If we want a bit more control, this is where we would have to go down the route of the 1D pump flow. So we use a 1D representation of the pump, and again we can have that constant flow. We can have those head discharge curves, or we can have a head discharge curve plus an operational capacity. So we can represent how that operates depending on different conditions.
Okay.
Sluice gates, again, we would represent using 1D structures. We can have various different flow modes. So we could have free flowing, where it's upstream controlled, downstream controlled mode, and also that transition between the two. Or again, we could have a head versus discharge at different openings. So we can use what's known as a QO channel to represent different head discharge relationships based on different conditions. There's always structures that don't quite fit into the assumptions or the other structure types. Whenever I would add in a structure for the first time, I would always recommend reviewing the manual, reviewing the various different structures. Where you have a structure that doesn't necessarily fit into the other structure types, where there's particular assumptions that aren't true, then we do have a couple of ways of representing them. One of which would be a Q-type channel. This allows us to specify an upstream depth discharge curve. So, quite a few structures, the operator or the manufacturer will have a depth discharge curve of how these structures should operate. Like I said, we can also have a QO type. So we specify an upstream depth and gate opening versus flow matrix. So the water, the transfer of flow will depend on both the upstream depth plus a gate opening and then a flow matrix. And then we can operate that gate. We can specify the gate speed, how quickly it opens, and also whether it is open, whether it's closed, or we can specify a percentage opening, and we can base that on upstream water levels or flow elsewhere or other structures. So we can use operational control to go through that. We also have M channels. So again, this is useful for structures which don't fit other structure types or specific assumptions. And this time, rather than just having an upstream depth versus discharge relationship, we've actually got a matrix of flows between the upstream and the downstream depths. So we define a matrix, and then basically that will then give us the amount of flow going from upstream to downstream. And we can also specify negative flows or negative values for flow going from downstream to upstream. So we've also always got a couple of different approaches to modeling those structures which don't fit in with the usual way of doing things. All 1D structures are set up within a 1D network layer, and the important aspect is the type. So we specify different type. So for instance, a P type is a pump, an SG type is a sluice gate, a W type is a weir. So there's a whole host of different types. And then the other parameters are defined on a structure by structure basis. And like I said, whenever coming into adding a new structure, I would always suggest reviewing the manual to work out what parameters are required, what assumptions have been made, and what each parameter represents.
Sorry, before you go too far on the structures, can we go back to the question from Quentin? Which is the good way to model a weir in a river? And I will add, if we don't have the elevation profile in the DTM, can we use a 3D break line or 2D break line with Z-shape with points? With
Yeah,
elevation points?
absolutely. So
this will be taken. Okay.
Yeah, that's it, exactly. So you would add a break line or 2D Z shape. That's exactly what's been done on this one here.
Okay.
So we've just used a thin break line in this instance, and then this is just a thick break line.
Okay.
So, and then that's that break line. The flow over the top of that uses the 2D hydrodynamics, and where it's weir flow, TUFLOW will automatically calculate that based on the advanced weir equation.
Okay. And a 3D polyline will work as well?
Yes. Yep.
Perfect.
It's doing it all on a cell face by cell face basis.
Okay. Thanks.
And also, we've always got the check files to go back and check the specification of those structures and make sure that we've got everything set up correctly.
Yeah.
Where we are using 1D structures, we just need to make sure that the 1D 2D link, which in the case of 1D structures would always be an SX connection. So we're taking the water level from the 2D domain, applying that to the 1D structure. That's calculating the flow through the structure. Then the flow's taken out of the 2D domain, and then at the downstream end, the flow from the 1D structure is applied to the 2D domain, back into the 2D domain. We use an SX connection. We just need to make sure that SX connection reflects the size of the structure. So in this instance, we've probably got two culverts going on. We've got one culvert which is less than the cell size. So we can do point coupling, and on this one, the culvert width is probably about 2 cells. So we've got linear coupling, selecting 2 cells that allow us to get the required flow into the culvert and also out of the culvert at the downstream end. So in this case, it's just 2 points at the upstream of the structure. In this instance, we've got a line, an SX line. We use a CN line to connect that to the culvert, and then we've got a CN line connecting back into an SX line. So these are the cells that are connected between the 1D and 2D domains. We can also, if we need to, add in polygons. So we can have a polygon that defines the 2D cells that are connected to this structure. Again, we use a CN line just to connect from the polygon to the 1D network. And in this instance, our polygon is selecting all those cells to allow us to get the requisite flow into and out of our structure.
So this kind of approach will work also on the lateral flux. If I have a road which makes some blockage, putting a polygon will allow to capture the flow in the direction of the bridge or culvert, and also laterally.
Yeah. So and any flow that gets into these cells will be allowed to go into that 1D network component, and then vice versa on the outside.
Okay.
We have the ability to do operational control. So this allows the user to operate any 1D structures, so sluice gates, gated weirs, pumps, etc. And what we do there is our type. So remember, we talked about setting the type to a P for a pump, or an SG for a sluice gate. We append an O to that. So an operational pump would be a PO, for instance. You can also use an OP, but I gotta be honest, I don't ever see that done. I think most people just use a P O for operation pump operational. And then we specify a rule ID in the inlet type attribute. And then that's what we specify here. So we define, in this case, a pump. We have PG pump specified within the inlet type, and then we specify our rules of operation. So we use a TUFLOW operational control file, and this allows us to define the various different controls. And the neat thing about using a rule ID is we can reuse this rule for multiple pumps if we need to. So that does help, particularly where you've got 4 or 5 pumps that are all operating pretty similar. Our TUFLOW operational control file contains 3 blocks of information. We have the default settings. So these essentially set the initial operation and also the default options. So, in this instance, the default capacity is 19.3. By default, the pump is off, or initially the pump is off as well. And the pump gets up to speed in 10 minutes. We then might have a series of user-defined variables. So this could be our upstream water level. It could be a water level in a location in a reservoir. It could be a flow through another link. It could be the difference in water level between 2 locations. It could be a time. It could be the operation of another structure or status of another structure. We define our user variables, and then we define our logic, which is essentially our ranges through which the pump or the sluice gate or the weir operates in different ways. So I always find it really helpful to draw this out as an image or a little table within Excel or similar, and work out the various levels that things are meant to switch on and off. You'll see here that if the water level is greater than 337.4, we switch the pump on. If it's less than 337.3, it's off. And there's what I call a dead band between them, 10 centimeters between them, where we have no change. And that what that stops is the pump or the gate oscillating between certain values. So it hunts between the rules if we don't have that sort of dead band in the middle. So I would recommend doing something along those lines. And these are some quite complex control logic in this instance. So there's 4 different locations. These are quite spread out. These were originally written without these nested statements. So we've got nested if statements, and I actually wrote these rules originally when I was back in consulting about 17 years ago, using InfoWorks RS, so using the ISIS engine. These were probably about 30, I think it was 28 to 30 lines of commands, maybe even more, and they had to be done for each structure. And there were like 50 odd structures. So we've simplified the logic here using the nested if statements, which are really, really powerful way of doing it. So you can add in some quite sophisticated approaches. In this instance, we've got the gate opening ++0. So what that means is the gate won't move. In this case, we're reducing the gate opening by 10 centimeter increments each time, and we're increasing the gate opening by 10 centimeter increments in this time. So we're not setting it to a set level, we're just increasing that gate opening bit by bit. Yes, absolutely. Just a note, if you are doing any operational control, then there is this _1d._o.csv file output that will give you the time varying status of any structures. It will give you the variable values, and it will give you the flow through that structures. Always really useful to plot that up and check that the operational control is happening in the way that you want it to. So in this instance, we've got the pump flow that comes from the 1DO file. We've got the upstream water level, which is our variable. And then I've just plotted on the switch on, switch off levels as well for this pump. And we can see, whether that's being picked up correctly in this instance. So always really useful to take a look at that file and plot things up from there.
Do you sorry.
So,
Do you have a specific way to track which rule is being applied? Because when you have a very complicated nested conditions, can be complicated to follow which one is really used.
Yeah, no, because we don't have rule names as such,
Okay.
because it is that, if else if statement. What you could do is actually have a variable, just call it like rule name. And for each rule, you just have like a rule name equals 1, 2,
Okay.
3, and then you can track it afterwards like that. So yeah, just use a user defined variable, which changes every time you're in a different part of the logic. Would be a good way of doing that.
Okay, so you can inject your own variable inside. Okay.
Yeah.
And sorry, second question. Is there some possibilities to pile on the operational rules? I was thinking maybe you can have a main model which has the specific rules for your system, and maybe you are doing some calibration with kind of specific rules for this event. Maybe some gates was closed and so on. Can you then call a first control file to say this is a nominal regulations, and then a second one which says this pump was not working, this gate was closed, and so on? Quickly.
Yeah, I think you should be able to do something along those lines using variables or events. Using scenarios, events, and variables. So you can have your base TOC file, and then you might just say if scenario equals calibration event 1, read this TUFLOW operational control file instead. I think that would depend on the specifics, but I'm pretty sure you'd be able to do something with scenario logic.
Okay, great. There were 2 questions. Do we keep them for the end, or
No,
do you want to address?
Go for it.
The one was from Nicola. How can we deal with velocities in the entrance, I guess, of the culverts with the connection with lines and polygons?
Yeah, so if we are connecting to the 1D domain, there is a representation of the transfer of momentum, but it's not a full connection. It's not a full representation of momentum as you're going into a 1D structure. There have been some changes to, I think it was one of the later releases of 2020, where we do take into account approach velocities. I'll be honest with you, I don't know the details of that, but it'd be worth taking a look into it, and I can certainly signpost those changes in an email. But we do there are some approaches of taking into account approach velocities. What I don't know is whether that's a default. So I will get some information on that and send through to you.
Okay.
It's been on my list to look into that in detail for a long time as well.
Okay, thanks. And a question from Quentin. What could be the difference between 1D weir and 2D?
They both use the same equations. They're both using that advanced. Well, no, you can specify different weir types in the 1D. Sorry, but you can have that advanced weir, approach in 1D as well. That gets used in the 2D. As a general rule of thumb, if you're modeling the riverbed in 2D, you want to try and keep the representation of the weir in 2D as well. Same with bridges. If you don't really want to switch back into 1D. So you could do it both ways. I suspect you would be able to get similar-ish answers, but the recommendation would always be to keep it in the same dimension.
Okay.
Yeah, that transfer of momentum across the 1D, 2D linkages as well would be valid in that instance too. Just, well, no, less important, but yeah.
Okay.
Finally, and apologies, I didn't realize this would take quite so long, so I will go through. This is the last lot of slides, so if you've got time to stick around, I don't see this taking more than about 15-20 minutes. But finally, just on breach modeling, a couple of different ways of doing this. The first, which we quite commonly use in benchmarking tests, for instance, is just to have initial wet cells in the 2D domain. You just have a water level set, and that just gives you that initial wall of water that we just let go within the 2D domain. Another approach is you calculate what the breach hydrograph would be and apply that as a flow time boundary. We can have variable geometry. So we can see here our embankment is changing in time. So we can have a variable Z shape, and then we can set that to have either a simulation time trigger. We say, right, the breach starts developing after 1 hour, or we could have a water level trigger. That development of that geometry or the removal of that geometry can be linear or non-linear. We can have what's known as a cascade approach. So this allows us to basically have a 2D boundary condition, which kicks in when a condition is reached somewhere else. So it could be that the water level in one location gets to a certain value, and then we apply a hydrograph somewhere else within the model domain. And then there's various 1D approaches as well, which I won't go into for the purpose of this webinar. In terms of those the variable geometries where it changes in time, this is done within a variable Z-shape layer. Just like any Z-shape layer, we specify a shape width, and then we specify a trigger value. So that can be the time in hours of that dam break. And then we have a period, and this is the time in hours over which the change in elevation occurs. And that's what we've got here. We just specify this variable Z shape, and we specify our shape width, and then we specify our trigger value, 1 hour, and our period, which is, this breach develops over the course of 15 minutes. We could have similar, but this time it's set up based on the water level. So we specify a trigger object in this instance. And then we specify a water level, which acts as our trigger. And then again, we have that period, that time in hours over which the breach develops, what have you. So in this instance, we've got a trigger called water level trigger. And then once our water level gets over 60 meters above datum, then our topography will start varying. I think that's spelled it. Then what we do is we have a VZ shaped point, and that's what acts as our trigger. So it doesn't have to be adjacent to the where we're varying the geometry. It can be somewhere completely different. So something like this can be used not only to represent a 2D breach in this, as is what's going on here, but we can also use it to represent, a gate or something similar. So we can have that gate going down. So we specify the trigger, we have the same name set up, and then we read them in conjunction with the variable Z shape polygon. We can also restore that embankment. So we can specify a restore interval as well, and a restore period. So, we can have that embankment breaching, and then, we might want to represent people getting out on site and fixing that back up, and, the period it takes to do that. And then we can set that to be repeated, so we can have it developing, coming back up. So that might be one way to represent that gate component, if we wanted to. If we do go down this approach, we can have the map output type of ZH, which allows you to plot the time varying topography or time varying bathymetry. So we can plot, this is a time series of the elevation value at that point. You can see we've got our breach developing, and then it gets restored afterwards. And we could animate that as well. So just as I showed you in that first animation, with our elevation values changing and being displayed in our map output as well. So you'll see at that point it will go from yellow and start moving to the pink and darker pink colors.
Okay.
And then once we start restoring that breach, then it comes back in and becomes more yellow. The cascade approach, we use a 2D source area polygon, or 2D source area trigger layer, and that gets linked to a 2D PO object. So what we have is a series of PO objects, and then we have this source area trigger polygon. And what we're going to do is, once the water level here gets to a certain value, we'll start to apply a flow or a HT boundary somewhere else within the model domain. This allows us, this was the way that we used to do things in the UK in terms of reservoir dam breaches, where we might have a reservoir upstream, comes into another reservoir, and you have that cascading reservoir, and basically they would breach one after the other once the water levels got to a certain level in an upstream reservoir. So that would allow us to cascade those one after the other. So, we could base that on water level, or we can base it on flow. So various different approaches to do it. Obviously, these have been benchmarked. Some of you might be familiar with the Malpasset test case, primarily used for, I think it was from Telemac and EDF. So this was a dam break, December 1959. Unfortunate loss of 433 lives. It's a commonly used data set based on a series of observations. So there were some electrical stations, and it was possible to work out the times of the flood peak based on when those stations got or essentially switched off. And a non-distorted flume model was created, which was used. The data set was pretty coarse, 20 meters, but as you can see, in terms of the flood footprint, pretty good representation within TUFLOW, and also in terms of the dam break front arrival time, based compared to observed values, they're pretty similar as well. So we've done a whole host of benchmarking with regards to breach modeling. One of the Environment Agency tests is 2D benchmarking tests. It's got some breach modeling examples and cases in it, which have been replicated, and others have done similar as well. It's not only water that we can model either. So one of the applications of TUFLOW more recently is using non-Newtonian fluids. So mine tailing dams is a pretty hot topic after the Bernardino catastrophe a few years back. So we can represent fluids with different characteristics. TUFLOW uses the Herschel-Bulkley approach model, or Herschel-Bulkley model, which is quite a flexible model. It allows the modeling of Newtonian fluids, non-Newtonian fluids, such as the Bingham plastic that we have there, and slurry. We can model a mixture of shear thinning and shear thickening fluids, and we can change the various densities associated with that as well. So if that's of interest, the 2020 release notes is really, really useful from that perspective. It's been added to over the last couple of releases, so it is now possible to have fluids of different characteristics mixing, although that does require an advection dispersion module license. But there's a whole host of information within the release notes, and also on our website is an article where we have gone away and replicated the Bernardino mine tailings dam failure. So that is it, which, you know, with a minute to spare is pretty good timing, although it doesn't leave much opportunity for questions. But I'm happy to stay online to answer any further questions. Again, similar to last time, happy to share the presentation. And I just will signpost that energy losses at structures webinar, which yeah, we've been running a whole host of webinars for the Australian Water School, which are really, really useful from some of these kind of things, and sharing the knowledge that's within the team to a wider audience. But happy to answer any questions.
Okay, there is already one, I think, from Quentin as well. If you can see this on the conversation.
Yep.
So to define location, yeah.
Yeah, so where the VZ shaped line is precisely where that breach will be. So obviously the line's giving you that spatial dimension.
Okay.
So yeah, so if you do have a breach which isn't necessarily uniform across it, then you would have to have different lines to represent the different elevations that it might get down to.
I think it was the example that was presented by the EA in the conference on all the work they have done on the
and the demountable
bridges.
flood defenses.
Yes. It was some kind of discretization of the defenses and then breaking one after the other. That's it.
Yeah, exactly. They would have been separate lines to represent, because what they were doing with this was temporary flood defenses, and you know, obviously they're of finite length. So they were saying, you know, what if this one failed or this one failed? So they were modeling those individually as individual lines.
Okay. Interesting. Any questions, people? I think we, as Duncan said, we will share the presentation. Question? No.
I see. Yes. Maybe one more question.
Yeah.
Back to Arch Bridge. So if I understood well, to modelize it, it's with the form of blockage. We have to estimate the blockage of the Arch Bridge under the deck, and that's it, right?
Yeah, that would be one way of doing it. The other way would be to model it in 1D. So there is that arch bridge approach. You can also use an irregular weir. I will double check, because one way of doing it might be to model it in 1D, and it provides some tables about the blockage. So you might be able to use the blockage from the 1D to inform the 2D blockage. So I'll double check that one as to whether that is feasible.
Okay, but it's available in 1D representation, the arch bridge.
Yes. Yeah.
Okay.
So let me never do things live, apparently, but let me see. I'll just load QGIS, because there might be something I can show you here very quickly. The QGIS is taking some time to load up.
No problem. It's the 1D NWK layer.
Yes. So it's set up as a 1D NWK layer, and it has the type B arch, which is a bit. I'll type that in the chat because it's specified as a type arch. But what you can do within the TUFLOW plugin is this new Arch Bridge editor. So we can set it up, we can bring in and import data from CSV file. If it is in an ISIS format, we can import that as well. And we basically bring in our cross sections. I'll specify cross sections. Let's see if I can do this. There we have our chainage versus elevation for actual cross section. How do I actually add a line? Okay, it should be possible to add in multiple lines here. Maybe. Yeah, that's not greatest. Let's see if I can add in multiple lines. No. So we specify our cross section anyway. Just say 14. Say 1, 9, 10, and then we specify our opening, and we can have multiple openings there. So let's say 1, 9. We specify a sprigging level, 10, and let's say the soffit's at 12. And I should be able to plot that up, and we can see our arch bridge in there. So this will generate it automatically, and we define, well, we set up a 1D network layer, and then that will set it all up with all the relevant files and generate those. So if you've got existing cross-section data, that can all be imported from a CSV file, etc., etc. So we can have multiple openings within that as well.
Okay.
Okay. Thank you.
Just very quickly, hopefully you are all using the QGIS plugin, and I would also recommend just keeping it up to date, because there's a really useful bit of functionality that's come out in the latest one, which is if you've got a TUFLOW layer. Let me just open up Notepad. If you've got a TUFLOW layer, or even a series of TUFLOW layers, what you can do is just right click on that, click TUFLOW, copy TUFLOW command, and then you can just copy this and paste it into Notepad++, and it brings in the command and it brings the layer, so you don't need to keep going back to the manual to find out what the correct command is for that particular layer. So it's a really powerful bit of functionality to make sure that you're getting the syntax correct. So ReGIS network, ReGIS BC, and where you're using lines, points, and polygons in conjunction, if you, I haven't got the data. Let me just see if I have got some data quickly to show you. This will work. There. So where you've got lines and points in conjunction, you can select those. Again, TUFLOW copy command, paste that in, and it brings in both layers and uses that pipe key. So basically we're using the points and lines in conjunction with each other on this situation. So really, really useful bit of functionality.
And this comes with the last version of the TUFLOW plugins?
Yeah, if you just go into the plugin and update it, it will be available.
Oh, very nice.
Okay. Any other questions? I think we have covered a lot of ground on the subject of structures. I think we can go quite far with TUFLOW on this representation of structures. So it's already useful to, I think, go a bit deeper in the manual as well, to understand really what we are doing with all of this. Thank you very much, Duncan, for everything. This was interesting, very interesting, especially on the I think on the this subject of 2D bridges, because I think it's becoming a very hot subject because we move a lot of old 1D models to 2D models. and a lot of questions arise on this subject. So thank you very much.
Thank you. And I'd just like to reiterate, if anyone knows of any studies or any data sets that would be useful from that perspective, we're, like you said, more and more people are modeling channels in 2D, and we're very keen to, develop the 2D bridge functionality and other structures as much as we can. So very keen to hear if anyone does know of any data sets or studies that would be quite useful.
Okay, I will pass the message also.
Super. Thank you very much.
Perfect. Thank you. Et bon appétit.